Welcome back to Applied Mathematics. In this video, I'm going to go through some area and volume formulas. Most of these formulas should be familiar to you. They should be things that you've seen previously. There's a couple that might be new, so I'll go through those in a little bit more detail, but by and large, I'm going to fly through these just as a quick review of what I expect you to know of geometric formulas before we move on to start using them in applications. There we go. Get my head out of the way here. And let's start off with a rectangle. A rectangle is the easiest shape I know. Remember that a rectangle is a shape that has 4 right corners. And we generally call the sides L and W for length and width. And if you know the length and width in one side, well, the other side has to match. All right, the top and bottom are both L, the left and right are both W. To calculate the area of a rectangle, we simply multiply length times width. Moving onward. The next shape is a parallelogram. There are a couple of different ways that you can define a parallelogram. My personal favorite is that the left and right sides are equal in length, and then the top and bottom sides are also equal in length, although not necessarily equal to each other. Another way you can define a parallelogram is that opposite sides are parallel to each other. That's where the name comes from. And it turns out that those two meanings are equivalent. If one is true, the other must also be true. All right. But to figure out the area of a parallelogram, you need the perpendicular height, right? Distance measured perpendicularly from one side to the other. And then you need the length of the side that you are measuring perpendicularly against. We generally call that the base. And the area is just base times height. One of the things I like talking about with parallelograms is that height measurement does not need to be inside the parallelogram at all, and it is still perfectly fine, and you can still do all of the same calculations. So if you have a leaning parallelogram like this, and you know the perpendicular height measured outside of the figure, and you know the base, which is just the part inside the figure, it's still the same formula, nothing has changed. Special case shapes. The square is a rectangle where the length and the height are the same. We generally call it the side length S. Every square is a rectangle. Not every rectangle is a square. So you just take length times width, but length is S and width is S, so you get S squared. I'm also going to mention here a rhombus. Much like you can think of a helps if I can draw this out. There we go. Much like you can think of a parallelogram as a rectangle that has kind of slid over, a rhombus is a square that has kind of slid over. So not only are the top and bottom equal, they're also equal to the left and equal to the right. There is nothing special about this as far as the formula goes whatsoever. We're still going to have to call this the base and we're still going to have to measure the height perpendicularly. Up next is the trapezoid. Trapezoids are a little bit challenging because there are so many different forms that shape can take on. The classic picture of a trapezoid looks something like this. We're going to call the distance at the top here B1 and the distance at the bottom here B2, and then figure out the perpendicular height between them. The two bases have to be parallel to each other, but the relationship between the other two sides can be whatever you want it to be. To find the area, you average the lengths of the two bases and then multiply by height. Right. Trapezoids, like I said, can be kind of weird because, again, they can take on so many different form factors and still count as a trapezoid. Right. Here is a trapezoid. It's kind of turned on its side, and it's also been set up in such a way that it actually has right angles on one side, so the height is a side of the trapezoid. That's weird. But it works, and that's the important thing. Moving onward, I tend to think of a triangle as a trapezoid where one of the shapes or one of the bases has kind of closed in. So just set B1 equal to 0. And then we can just call it B instead of calling it B2. And the area is B over 2 times H. When you have a right triangle, it certainly makes that process a little bit easier because the perpendicular sides are actually the outer edges. All right, so if we name the right triangle using the same variables we would use for the Pythagorean theorem, we can say that the area is 1/2 times A times B, and it's just the same formula with different variable names. But what if you don't have either of those cases? Your triangle is not a right triangle, and you don't have a perpendicular distance to the point inside the triangle. Well, that's where Hero's formula comes in. I've seen his name spelled H-E-R-O. I've seen it spelled H-E-R-O-N. I've heard it pronounced Hero, Heron, Heron, and Yerin. But I think he's most known as Hero. Hero of Alexandria was a prolific inventor in the age of antiquity. He worked at the fabled Library of Alexandria, and he did clockwork mechatronics. He was responsible for a lot of the ancient inventions of moving animatronic lions and things like that. He did a lot of work in hydraulics, and one of the formulas that he is most well known for today is his formula for calculating the area of a triangle when you don't know much about it. So if we have a triangle, it is not a right triangle. We don't know anything about a right angle, but we know that its sides are A, B, and C. Well, the perimeter is A plus B plus C. That's easy. I want to take the perimeter and divide by 2. That's going to be a new parameter, which we call s. To calculate the area of this triangle, we're going to take the square root of s times s minus a times s minus b times s minus c. If you're really curious, I can send you a derivation of where this formula comes from, but I don't find that it's useful to look at, so I've stopped going through it in general. But let's go ahead and fill in this particular triangle. And let's go ahead and say that the sides of the triangle are 12.9 centimeters, 13.1 centimeters, and 13.3 centimeters. Well, if I add those together, I get 39.3 centimeters as the perimeter. I want to divide that by 2, and I get that s is 19.7, right? 19.65, but I'll round it to 3 significant figures, call it 19.7 centimeters. Now I want to take 19.7 centimeters. I want to multiply it by 19.7 minus 12.9, which is 6.8 centimeters. I want to multiply by 19.7 minus 13.1, which is 6.6 centimeters. And I want to multiply by 19.7 minus 13.3, which is 6.4 centimeters. All right, multiply all of that together, I get 5,658, but I actually only have 2 significant digits now, so I'm going to call it 5,700. And I have centimeters to the 4th power. That's nasty. Luckily, I am taking the square root of that. Round that to 2 significant digits, and I get 75. And then the square root of centimeters to the 4th power is centimeters squared, right? Centimeters squared times centimeters squared would give you centimeters to the 4th. And that is exactly what we expect for units of area. So at least that's one thing that seems to work out in our favor. All right, moving on. I don't know why I'm bothering to draw a circle, but we know that the formula for the area of a circle is pi r squared. One of the interesting things that we can work with in a circle is using the area and also the circumference in the same problem. One of the challenges of working with circles is that measuring the radius is incredibly challenging. So whenever you're working with a circle, the general rule of thumb is take whatever you're given and use it to figure out the radius, and then use the radius to figure out what you actually need to know. For example, calculate the area of a circle whose circumference is 20.0 feet. Well, since the circumference is 20.0 feet and circumference is 2 pi r, that means that the radius is the circumference divided by 2 pi. which my calculator is happy to tell me is 3.18 feet. Be careful punching that into your calculator. Make sure that you're dividing by both 2 and pi here. That is an easy place to make a mistake. And then the area is pi times the 3.18 feet that we just calculated squared. So pi times previous answer squared. My calculator is going to tell me that that comes out at 31.8 square feet. All right. Hopefully nothing too crazy there, but being able to work fluently with a couple of different measurements in a circle in the same problem can be tricky if you're not practiced with it. Moving onward to 3 dimensions, cylinders and prisms. A prism is a shape, a 3-dimensional shape that has a straight-sided base to it and vertical edges such that the top and bottom are the same shape. A box is a classic example of a prism. A cylinder has instead curved shapes on the top and bottom. Other than that, it is the same idea. But you can treat the top and bottom as a 2-dimensional shape, calculate its area, and then measure the height, the distance perpendicularly from the bottom to the top, and the volume is simply the area times the height. So if you have a box, a rectangular prism, well then the area is length times width. If you have a right circular cylinder, the area of the base is a circle. The area of a circle is pi r squared. And you can continue on with any other shape that might show up. Similarly with cones and pyramids. A cone or a pyramid is either straight-sided or curved-sided base, where instead of having straight sides, it meets at a point. And if you measure the perpendicular height and the area, the volume of one of these is 1/3 times the area of the base times the height. So if you have a rectangular base pyramid, then the volume is going to be 1/3 length times width times height, because length times width is the area of a rectangle. And if you have a circular base cone, then the volume is going to be 1/3 pi r squared h, because pi r squared is the area of a circle. I've never seen a shape that had a straight edge base and still formed a dome, but I guess in theory it could exist. Right, but if we have a circular base, and instead of coming up to a point, it comes up to a circular radius, we can again measure the height perpendicularly, we can figure out the area of a base, and the volume here is 2/3 times the area of the base times the height. Again, for the circular case, the area of the base is pi r squared. A sphere is just a dome on the top and a dome on the bottom. So a sphere would be twice 2/3 pi r squared h, although I guess also in this case, h would be r, so it would be 2 times 2/3 pi r squared r, which comes out at 4/3 pi r cubed. Again, I know I keep hitting the wrong button. I apologize. I know I flew through a lot of those formulas. I really hope that most of those formulas will review for you. They should be things that you are at least familiar with, and hopefully this has jogged your memory of any of them that you may have forgotten about. The general case of prisms, cones, and domes, we will be looking at a little bit later on in the course. One of the things that is still yet to come is, well, what if you don't have one of these nice shapes? What if you have an irregular surface, or an irregular shape on a surface, or an irregular volume in space? We'll develop some tools for calculating the areas and volumes in those cases, and it will revisit that generic idea for the volume of a dome or a cone or a prism. But for right now, I think that's far enough, so I'll wrap up with this. Thank you as always for joining me, and I'll see you in the next video.